communication is not just about sending a message, it's about the journey. So whenever a sender is sending a message, it's propagated to the path, and all the time it gets attenuated and distorted. So our project mainly focus on how we can successfully extract our message signal from this noisy environment. So Assalamualaikum and good morning everyone. Welcome to our project, which is the design of 2.45 GHz direct receiver in CMOS 45 nanometer technology. So before I go to further details, I would like to request all my team members to introduce themselves. Myself, Ajay Sweeto.
This is Shubham Kormakar. This is Mohammad Tahammud. This is Shahid Hussain.
Thank you everyone. Here is our table of contents. So rather than extracting our message signal, what are the other reasons why our direct receiver design matter? If I simply put it in one or two sentences, I can say that in today's world, there are continuous demanding for compact and low power devices. So by using 45 nanometer technology, we can design more compact and efficient system. This system can be implemented in wired Bluetooth or any other wearable devices. This is the basic diagram for our RF receiver, where at first we use a bandpass filter to isolate our desired signal and cancel out all the interference. And then we use an array to boost our low power signal, and then this output fed into the input of the mixer output down converter signal into a high frequency signal and a baseband signal. Then finally to extract our baseband signal, we use a low pass filter. So before going to our design procedure, we did some literature review, and on the basis of those literature review and sitting with our vendor, we proposed some improvements, and those are the specifications for our blocks. So we designed our RF receiver with the passive low pass filter design, and here is our circuit. Though the SNL analysis ensures all the specification, but there are some limitations in passive low pass filter design, such as there is no gain control, or since those are discrete components, they need more size. That's why we move into the active low pass filter design. For active low pass filter design, we use GMC topology. For GMC, we use 5 transistor ODI. Here, this GMC will work as a resistance so that we can control the pole in the output node. This is our schematic diagram of our first order active low pass filter design, and the DC analysis confirms that all the transistor operates in the region 2, and the power consumption of this circuit is 0.15 kilowatt. Here is our control analysis and AC analysis. AC analysis shows that we have a cutoff frequency of almost 20 MHz and the 20 dB attenuation. And then finally, cascading to first order low pass filter, we create a second order filter. Here the cutoff frequency is 20 MHz, but now this time the attenuation is 40 dB per decade. That's it from my side. Now I will request Shubham Kormakar to continue from here.
Thank you, Ajay. Now the discussion begins with the mixer block of the receiver circuit. The fundamental purpose of the mixer circuit is to take a very high frequency. In this case, we use 2.45 GHz and convert it into a lower frequency called intermediate frequency, and this process is also known as the down conversion process. And as shown in the slide, in the diagram, we see that this mixer is done by the multiplying two frequencies. One is the RF input signal and another is the local oscillator. And both these can determine as two new frequencies, which is the sum frequencies and the difference frequencies. But in this case, we use the difference frequencies, which is the IR signal, which we want to capture. That to implement this, we use the most common and effective topology called the universal mixer. It consists of two typical parts. It's differential amplifier, which is called the RF input signal, and another is the cross-coupled switching cord. It actually does the local oscillator, that is driven by the local oscillator. So next, here is the design calculation for the mixer as shown here based on the case specification, where we show required component values, and this is the complete universal schematic design. We ran several analyses like DC analysis. In the DC analysis, we get the saturation in the most saturation, and the power consumption we made 2.5 milliwatt. Then going to the next slide. it is the transient analysis process which confirm that our mixer performing well, and the conversion rate we achieved was 15 dB. The next critical part is the low noise amplifier. The main role of the low noise amplifier is to amplify weak received signal while adding minimum noise. Then coming to the next slide, here is the theoretical equation for the low noise amplifier. Based on the 45 nanometer CMOS technology process, we calculated different values shown in the this slide for inductance, capacitance, and the transistor dimension to optimize the performance. This is the complete circuit diagram for the low noise amplifier. We use single stage cascade topology with inductive source degeneration, and in the DC analysis we get power consumption with the 0.8 milliwatt. In the AC analysis we get the maximum gain of 23 dB, which is required our specification, and the stability factor we get is greater than 1, which is 3.27 dB, and the noise figure we achieve 2.3 dB. We further shown the transient analysis, which also amplified the standard signal smoothly with a gain of 16 dB, and we ran several analysis like parameter analysis, which can show the input and output impedance matching. And moving to the performance summary slide, here is our complete result for the LNA. It's showing the simulation results where meet our requirement, such as gain, which is we take it 15 to 20 dB and we get 20 dB result, and then we get of S parameter analysis, S11 and S22 and other parameters, which we also fill up our requirement. Now I request our Thermal to continue from the next part.
Now I am going to explain our bandpass filter. As our previous member have already explained, traditional inductors have resistance loss, and as well as they also take so much area in lab. We have decided to go for our 2.4 GHz bandpass filter using a gyrator-based active inductor. As you can see here, our gyrator head is basically a differential curve. This is the positive half and this is the negative half. So I am just going to explain the first half or the half circuit. The core of our filter is the central acetate node, and we cannot just put the RF input voltage into this node because this acetate node has a massive impedance at resonance. So we have used this ME transconductor to convert our input voltage into an AC current that pumps straight into the tank. Now for the LC tank to resonate, for the capacitance we get by all the parasitic capacitance from all the transistors connected to this central node, and the inductance we get by our gyrator uses two transconductors, this differential curve and this common source amplifier in a negative feedback. Now by delaying and inverting the signal, our gyrator node forces the AC current to lag the voltage in this specific node by 90 degrees, which perfectly mimics a real inductor. We also have tunable functionality with this MI director, by which we can change the center frequency of our bandpass filter. Now you might ask why the current found by this ME transistor doesn't also escape into this MO transistor. We have designed this for solar buffer, which gate actually works like an open circuit. It also allows us to isolate our LC tank so that heavy load doesn't destroy our Q factor and also detune our frequency. Now, if I show you the result, in AC analysis we see this, the peak is at exactly 2.45 GHz and the gain is 36 dB. And if we go from lower from there at minus 3 dB point at 33 dB, our frequency is 2.47 GHz. That means our bandwidth is 20 MHz, which was expected. Then to show our bandpass filter only allows 2.45 GHz, we have used three frequency components here: 2.45 GHz, 5 GHz, and 10 GHz into the input, and in the output we only get 2.45 GHz. But it is still not clear, so we have used DFT analysis. Here we can see there are three frequency spectrums: 2.45 GHz, 5 GHz, and 10 GHz that we put into the input of our bandpass filter, and in the output we only see 2.45 GHz. After that, we have integrated all of our RF blocks, and we have also used MATLAB code to simulate our modulated signal, because our cadence don't have any keyboard function for that. And to show the result, I will invite our next member, Sadhu. Thank you.
Thank you, Dawar sir. Now I will discuss about the total result of our RF receiver block and the functionality of our receiver. So first we move to the talk about the DSPC subtype carrier transit analysis, and here we use the message signal of 10 MHz, and the carrier frequency is 2.45 GHz with a 50 microvolt amplitude. And let's see the graph that how the signal moves through the individual each block. First, the bandpass filter only picks the 2.45 GHz, and after that, LNA boosted up and the mixer down converted those frequency into a baseband frequency or a low component. After this signal passing through a low pass filter, we got our 10 MHz signal back, and when we measure the output of our output signal, we get that our gain is 50 dB, which is 320 times higher than our input voltage. And we also analyze the DFT analysis to confirm and ensure that our RF receiver block working perfectly. So now let's talk about the signal quality and the linearity analysis of our RF receiver block. In the DFT analysis, it shows that our signal is more distant than the noise is here, and we get the SNR from the DFT analysis is 49 dB. That means our output is more reliable. And in the linearity analysis, we find that our input range is 1 microvolt to 1.3 millivolts. This is a wide range of input volt that can ensure that our RF receiver design is reliable. And next, to analyze that our RF receiver only pass through the 2.45 GHz and block the other frequencies like 5 GHz, 10 GHz here. So we did a frequency divided multiplication analysis, and we get that in DFT analysis, here is the message signal with the 2.45 GHz spectrum and the 5 and the 10 GHz. And after the bandpass filter output, we just got only a 2.45 GHz signal which we desired. And the LNA boosts the signal, and the main work for the is our mixer. The mixer down converted it into convert to a two spectrum, like one is a sound frequency which is 4.9 GHz, and the another one is a difference component which is a 50 MHz output. And the LPF cleans the signal of 4.9 GHz because we need the desired message signal 50 MHz in the output. So after LPF, we get our 50 MHz signal back. So let's talk about the output summary. We get our interface structure is power consumption is 6 milliwatt, and the total harmonic distortion is 1.3%. This is a very good for a RF receiver, and we get our SNR is 49 dB. So move to the our interface and Q-phase structure. Here we show that our power Here we show that our power consumption is increased slightly because we add another mixer and another LPF in the Q-phase structure. So to verify this, we analyzed a transient analysis and got that our output is perfectly 90 degree phase shift in the analysis. And after that, we analyzed the reproduce pattern to show that it has a perfect 0 degree phase shift because we find out a perfect circle in the reproduce pattern. So we use the modern tools like Cadence and the MATLAB. So it can be a PO5, and we have designed and successfully complete our design. It can align with the PO2, PO3, and after when we designing this problem, we got some problem, and after we solution this, so it is aligned with the PO5. Here is the comparison table of our RF receiver block, and in conclusion, we have successfully designed our 2.45 GHz RF receiver, and with the power consumption less than 10 milliwatt, and the total harmonic distortion is close to 1%. And thank you all of you to join with us. Now we are open for any type of question.